Classical mechanics assumes a particle's future is determined by its position and momentum. To model the atomic scale, we replace Newton's second law with the time-dependent Schrödinger equation. The central variable is the wave function, psi, the mathematical construct carrying every piece of information about a quantum system. This split-screen comparison shows the predictive gap. On the left, classical mechanics identifies a single exact trajectory. The position at any future time is an absolute certainty. The right side illustrates Max Born's statistical interpretation, describing the particle as a distributed wave. We calculate the probability of finding a particle within a region, defined by the area under the curve of the wave function's absolute square. This indeterminacy is the foundational reality presented by David Griffiths in Introduction to Quantum Mechanics. Our mathematical journey through this system relies on the strict application of Hilbert space and operator formalism. Understanding this landscape requires us to move past macroscopic intuition and follow the specific rules governing symmetries and perturbations. To find measurable quantities, like position or momentum, we calculate an expectation value. This integral provides the statistical average of the outcomes we would see after repeated measurements of the same state. Within this integral, classical observables are represented by Hermitian operators. These operators act on the wave function to yield a real, measurable result. Consider a case study where a particle exists in a linear combination of two stationary states. The evolution of this system is dictated by a relative phase constant, phi. An overall phase factor doesn't change measurement outcomes, as it cancels out in probability calculations. However, a relative phase constant creates time-dependent interference. As phi cycles, the probability density curve shifts. This directly moves the particle's expected position, tracked here by the oscillating vertical marker. In quantum superpositions, the relative phase is the specific mechanism that drives the system's dynamic behavior. If operators determine the properties we observe, we must identify the mathematical constraints that govern the operators themselves. A symmetry is a transformation leaving the Hamiltonian invariant. This happens when its operator commutes with the Hamiltonian, evaluating to zero. Applying the time evolution operator proves that if an operator commutes, its expectation value remains constant. Spatial translation yields conservation of momentum. Time translation yields conservation of energy. Rotational symmetry conserves angular momentum. These conservation laws are the inevitable results of the continuous mathematical symmetries present within the Hamiltonian. While some symmetries are continuous, others are discrete, such as parity. This is the instantaneous inversion of all spatial coordinates through the origin point. Parity lets us evaluate the electric dipole moment operator, which dictates atomic transitions. The operator is the product of charge and position. Since inverting position negates the expression, the dipole operator is considered odd under parity. Laporte's rule applies this logic to atomic transitions. If you attempt to calculate the transition between two states with the same parity, the odd symmetry of the operator forces the result to zero. The transition is mathematically impossible. These vanishing integrals establish our selection rules. They determine which quantum transitions can occur and which are prohibited by the system's symmetry. Perfect solvable models like the harmonic oscillator are rare in nature. Real-world atoms are complex, interacting systems that require a different approach. To model these systems, we use perturbation theory. We start with a solved base state, the unperturbed Hamiltonian, and add a time-dependent term to represent the interaction. This process is complex in degenerate systems, where multiple states share the same energy. In those cases, we must project the Hamiltonian onto a specific subspace to define the correct starting states. For a transition to occur, the perturbation must fluctuate. Consider a Gaussian pulse, a bell curve perturbation that increases and fades. Before the pulse, the probability of the upper state is exactly zero. By integrating the pulse's effect over time, we calculate the transition likelihood. As the bell curve sweeps across the system, the probability of excitation rises, driving the particle toward the upper energy level. This framework allows us to model the dynamic events that occur in systems where an exact solution is unavailable. The localized behavior of an individual atom differs from the chaotic interactions of macroscopic objects made of 10 to the 23 constituent particles. Quantum mathematics allows for superpositions. Yet our macroscopic experience is restricted to singular, clearly defined states. This tension is visible in the EPR paradox. When two particles are entangled, measuring the spin of one reveals the spin of the other instantly, regardless of the distance between them. This creates a perfect correlation, but it does not allow for signaling. Because the local observer cannot control their measurement result, they cannot use this connection to transmit a signal. Thus, the principle of locality is maintained, and information does not travel faster than light. The disappearance of superpositions at the human scale is explained by decoherence. A macroscopic object is under constant chaotic bombardment from its surrounding environment, from colliding air molecules to stray bouncing photons. These environmental interactions act as a continuous measurement. This process mathematically degrades the wave function, forcing the broad superposition to collapse into a single classical spike. Quantum mechanics describes a probabilistic universe that reduces to a deterministic classical world under the cumulative weight of environmental decoherence.